Hello everyone, my name is Nadja Steiner. I'm a research scientist with Fisheries and Oceans Canada, and I would like to talk to you about model projections of Arctic ocean acidification in regional and CMIP6 models. I would like to acknowledge my co-authors Joe Langer, Kathy Reeder, and Tessa Su. As an introduction, I would like to highlight that 2021 was a year of assessment reports. Earlier this year, we had the AMAP Arctic Climate Change Update 2021. This report highlights that the physical drivers of Arctic change continue to change rapidly, that extreme events in the Arctic are changing in frequency and intensity, that climate change is having major impacts on Arctic communities, that ecosystems are experiencing rapid and transformational changes, and these changes have global consequences, and that the latest climate models continue to project that the Arctic will warm rapidly over the course of this century. These results are essentially echoed in the recent IPCC sixth assessment report, and have also been shown already in earlier assessments report as well as in the special report on the ocean climate and cryosphere. The key message of the recent IPCC report really is that the message is the same, but the certainty is decreased. In addition, we had the IPCC workshop report on climate change and biodiversity published in June, and that one highlighted that we cannot look at climate change independently but have to look at climate change and biodiversity as well as societal impacts together, especially if we look at adaptation and mitigation efforts. On the right-hand side, we can see the surface temperature in the most recent IPCC IR6 report, and then the decrease in sea ice for all the different scenarios, as well as a strong decrease in pH. And here we actually do see quite a difference depending on which scenario is followed over time. Global climate models remain the main tool to look at model projection, and this is an example from Xu et al. For sea ice in CMIP5 and CMIP6 models. What they highlight is that there is little change from CMIP5 to CMIP6. The models reproduce the seasonal cycle. CMIP6 shows a slightly lower intermodal spread in sea ice extent but a larger summer bias. The observed Arctic September sea ice extent decline is slightly underestimated, and the CMIP6 models did not reproduce the summer tendencies after 2000. This includes a faster decline in the Arctic sea ice extent, which is induced by spatially constrained acceleration in the pace of melt in the more Siberian seas. But it could also be related to internal variability in the models. So we know that climate change is proceeding with a faster pace in the Arctic than anywhere else, about 2 to 3 times the warming, most advanced ocean acidification, as well as sea ice decline. However, change is not uniform across the Arctic, so we are looking at some regional subdivisions to look at those changes over the regions. What we are seeing here are some earlier results from my previous student Erik Mortensen, looking at ocean acidification from 1980 to 2015 in a regional ocean ice biogeochemistry model. We are seeing the increase in PCO2, decrease in pH and omega aragonite, and some higher variability and slow decrease in ice cover. What we are also seeing is like a clear or distinct regional differences with the lowest pH and saturation stage in the Laptev Sea, and also very low values in the Beaufort Sea, with higher values in the Atlantic-influenced Norwegian and Barents Sea. We have now run this model into the future and showing that the projections indicate a continuation of the past trends with some reduction in the regional differences. So we're seeing again PCO2 increasing, the pH decreasing, with some decrease in the range over time, along with the decrease in sea ice cover. For the pH, again, we are seeing the lowest pH states for the East Siberian Sea, with also some lower states in the Canadian Arctic and the higher values in the Atlantic inflow. However, this represents only one model and gives us little information on uncertainty. So we have been looking at CMIP6 models, and we chose 9 models based on the available variables in those models. We're also looking at vertical depth averages based on species assemblages which have been identified in the Beaufort Sea Marine Fishes projects. What we are seeing here are the results for omega aragonite for 4 different regions: the Canadian Polar Shelf, the North Beaufort Sea, the Chukchi Sea, and the Laptev Sea, again using an average over the top 60 meters. And what we are seeing is mostly a large bias, especially at the beginning of the model runs, but then we do see a decrease in this range of models over time, and that's consistent for all the models. We also do see some consistency that the models that are more on the lower side remain on the lower sides for all of the models, with a few exceptions. For example, in the Laptev Sea, we see one model that is very high in saturation state, which is more like in the mean region for the other regions. But we also recognize that we can't look at ocean acidification on its own. So we need to look at other stressors like temperature specifically, but also oxygen, for example. And what we're seeing here is for the 2 regions, North Beaufort Sea and Laptev Sea, the temperature evolution for the different models. Here we actually see that the model are fairly constrained at the beginning, but become much larger in their range over time. And we see that also reflected in the oxygen, because again, this is the upper ocean, which is highly influenced by the temperature-driven solubility. Shown here is the multimodal mean for omega aragonite on the left and omega calcite on the right, again for the top 60 meters, and for all the different regions. So what we see here is a large spread among the regions, especially at the beginning of the time period, but we do see that over time the spread among the models is reducing and they become closer together. We do see a consistency among the regions, that they all maintain most of their bias over time. And we also see that the same picture before, that we have the East Siberian Sea as the most advanced ocean acidification, and North Atlantic influenced Barents Sea and Nordic Sea with the higher saturation states. This is again the multimodal mean for the various regions for temperature on the left and oxygen on the right. We are seeing here again large differences. Unsurprisingly, we see much higher temperatures for the regions that are more southerly, like the Bering Sea, Barents Sea, and Nordic Seas. And that is also reflected in the oxygen, as this is the upper ocean oxygen and temperature. That's of course strongly influenced by the temperature-dependent solubility. In order to provide a more policy-relevant visualization of the results, we created these heat maps showing all of the regions over time, and the colors indicating the number of models crossing a certain threshold. For omega aragonite, this is the saturation state of 1, and we do see still the large variability that has already been pointed out. But we also see that there is fairly consistency in the individual region of when the models cross a certain threshold, at least in most of the regions. We also see that most of the regions reach a state of undersaturation over the course of this model runs. On the right-hand side, we see temperature with a threshold set to 5 degrees, which has been chosen based on the seasonal variability and a threshold for Arctic cod in a certain time of year. And here we're seeing that threshold is only in a few places crossed yet. But in the core of the northern Arctic regions, it's only late in the century that threshold will be crossed. We were then trying to put multiple stressor information into one of those heat map figures where the colors indicate combinations of thresholds crossed. In this case, we are seeing that the omega aragonite is the key stressor crossed early, and there is only a few regions where the set temperature range is crossed. Oxygen does not seem to be the stressor, at least not for the upper surface layer, which is not surprising. So in summary, climate change is faster paced and more advanced in the Arctic. International assessments continue to repeat their message with more certainty and stronger urgency. CMIP6 evaluations are expanding, however, uncertainties representing sea ice remain. The models show consistent projected trends, but bias among models. For omega aragonite, biases uncertainty decrease over time. For temperature and oxygen, uncertainty increases over time. There are clear differences among Arctic subregions, both in historical times and the future projections. The AMAP recommendations, which have been reiterated in IPCC, best IPCC reports, continue to apply: limit future change, expand monitoring and documentation of Arctic change, and address information gaps, improve relevance and availability for scientific information for decision making. Thanks very much for listening.